Hi and welcome back to clip number 3 of 4 discussing nucleophilic addition elimination mechanisms. In the first clip I gave a generic overview of the addition elimination mechanism, and in the second one we looked at some specific examples with acid chloride reactions, taking into account their reactions with water, alcohols, ammonia and also primary amines. In this third clip, we're going to change the starting material this time, but this time look at acid anhydride reactions. An anhydride reaction being a carbonyl, no difference there, but the starting material is slightly more complicated by the fact that A, it's larger, and B, it doesn't simply have a chlorine or chloride leaving group. It has this larger leaving group on the right hand side. But fundamentally, as we've said in all of the examples so far, the underlying mechanism doesn't change. So I'm going to use methanol as my nucleophile. I'm going to just use one alcohol example this time. This clip's not going to go through ammonia and water and primary amines. However, hopefully now we can see that it doesn't matter what that starting material is down here, that R group is fairly independent of the reaction mechanism. It just changes the name and structure of the final product, but the reaction mechanism itself is largely unchanged. We still get this initial nucleophilic attack step, which opens up the carbonyl group and then allows the mechanism to proceed in exactly the same way as we have seen it before. The problem with acid anhydride reactions, relatively simplistically, is they are just a lot more complicated to draw of the intermediates, because there's a lot more things to draw and you very quickly run out of room. But ultimately they do exactly the same thing. The first nucleophilic nucleophilic addition step opens up that carbonyl, allowing the second step to then, as we say, do exactly the same as the generic mechanism did, allowing the molecule to then subsequently do that, dropping off the proton again. So the H plus will come down off that molecule. This, in this example, will create an ester, again, as we did in the second clip. But this time, what we get is, so the product becomes exactly the same product as it was when we used an acid chloride. So the product of these two reactions doesn't change. We will always generate an ester in this example when we're using an alcohol reacting with either an acid chloride or an acid anhydride. So this methyl ethanoate product is exactly the same as it was when we reacted methanol with ethanol chloride in clip 2. The only difference now though is that this leaving group is substantially different to the simplistic chloride that we lost off in the second clip previously. And what we end up with is the ethanoic part of that molecule coming off here as an ethanoate, which is then able to combine with this proton here, giving us ethanoic acid. So ethanoic acid is a byproduct of ethanoic anhydride nucleophilic addition elimination reaction mechanisms, whereas in the acid chloride reaction mechanisms, the side reaction or the side product was HCl. The difference here now being that HCl is a strong acid, whereas ethanoic acid is a weak acid. And industrially, that makes a big difference. The production of a weak acid means that the product mixture, the reaction conditions, are less corrosive and less hazardous due to the weak acid product being formed as opposed to the strong acid being formed. But ultimately, in terms of what we've actually produced, in terms of the fundamental chemistry, this methyl ethanoate product is exactly the same product as if we had made it with ethanol chloride, as we did in clip number 2. The fundamental mechanism is still this nucleophilic addition step at the beginning, followed by this elimination step in the second step. And I did miss off the arrow there, which would then allow that second molecule to get kicked out. So thank you for listening. We'll look at, in the final clip, a slightly more complicated set of examples, but again, ones which are fundamentally nucleophilic addition eliminations at heart, that being polymer reactions of condensations for polyesters, and also looking at some very simple biological applications of polyamide reactions as well. So that will be in clip number 4. Thank you for listening, and I'll see you next time.